Hello, I am your host today, and welcome to the Animated Scholar. Today, we're going undercover, deep into the world of mathematics to unmask one of its most mysterious characters, the complex number.
So, let me ask you something. How can one single number tell you not just how much, but also where to go and how far? It sounds kind of impossible, right? Well, that's because complex numbers contain a secret set of instructions, like a hidden map, and today we're going to learn how to read it. All right, let's meet our person of interest. This is a complex number. It's got two parts. First you have A, the real part, the numbers we use every day. Then you've got B, the imaginary part, and it's always attached to that very special symbol, iota. Put them together, and you get one seriously powerful number. Now the cool part is that all the clues to understanding these numbers are hidden in plain sight. They're right here, inside these math problems from our source material. We're going to use these very questions as our guide to crack the code. Every good secret agent needs a cover story, a disguise. Well, the first identity of a complex number is what we call its rectangular form. Just think of it as a number pretending to be a simple set of coordinates on a map.
See, that A plus B iota thing isn't just some abstract formula. Nope, it's a direct set of instructions. It says, start at the center, move A steps sideways, and then move B steps up or down. It's really that simple.
Let's grab a real example from question 9 in our source. A particle's position is given as 2 plus 3 iota. What does that mean? It literally just means go to the coordinate point 2, 3. 2 steps to the right, 3 steps up. Boom, the first disguise is just a location on a grid.
But what if you don't want to walk in that L shape? What if you want to know the most direct path as the crow flies? Well, for that, our complex number reveals its second, and I'd say true identity, the polar form. This one is all about distance and direction.
So instead of thinking go over and then up, the polar form tells us to point yourself in this direction and then walk this far. It gets you to the exact same spot, but in a much more direct way. Here, r is that straight line distance, and theta is the angle you need to turn.
And here they are, side by side, the two secret identities of the very same number. On the left, you've got the rectangular disguise, perfect for anything on a grid. And on the right, you have the polar identity, which is amazing for anything that involves rotation or a direct distance.
The real magic, of course, is being able to switch between these two identities. So how do we do it? How do we take a number in its simple rectangular disguise and reveal its true, powerful polar form?
Let's actually do one from question 1 in our source material, 2 plus 2 root 3 iota. Okay, so first we need to find r, that direct distance. We call it the modulus. Then we find theta, the angle, which we call the argument. It's really just a bit of simple trigonometry to find the shortcut across our map.
So first up, we calculate the modulus, r, that straight line distance. And for our example, it comes out to a nice clean 4. So that tells us our point is exactly 4 units away from the starting point.
Next, we find the argument theta, our direction, and that calculates to pi over 3 radians, or if you prefer, 60 degrees. And just like that, we've revealed the secret identity, a distance of 4 at an angle of pi over 3.
And hey, guess what? This isn't a one-way street. If you peek at questions 2 and 6 in our source, they're all about doing the exact reverse, turning that polar form right back into the simple rectangular map coordinates. It works both ways.
Okay, this is all pretty cool, but you might be thinking, why? Why does any of this matter? Why would a number need two identities? Well, my friends, this is where complex numbers stop being just a math problem and start having actual real-world superpowers. When we look at our second source image, we start to see questions about physics and electronics. And here's the kicker. The reason we need both forms is that some real-world problems are incredibly difficult to solve in one form, but they become shockingly simple in the other.
And this brings us right to question 8. Anytime you need to describe something that vibrates or oscillates, like a sound wave or a pendulum, the polar form is just a natural fit. The amplitude, which is how far it moves, is simply r. And the phase, which is where it is in its cycle, is just theta. It's like it was born to describe waves.
Or how about electronics? If you've ever dealt with AC circuits, you've run into something called impedance. It's basically the total opposition to the flow of electricity, and get this, it's a complex number. It has a real part, resistance, and an imaginary part, reactance.
And this is exactly why engineers love them.
Look at question 10. We see that both voltage and current are being represented as complex numbers. To find the total opposition, the impedance, all you have to do is divide one by the other. It turns a really tricky calculation into simple arithmetic.
So, when you get right down to it, complex numbers aren't just some mathematical curiosity. They're the native language for describing some of the most fundamental forces in our universe, from the tiny vibrations in an atom to the very electricity that's powering your screen right now.
Which leaves us with a pretty fascinating thought, doesn't it? If these numbers with their secret identities are the key to understanding waves and electricity, what else are they the key to? Quantum mechanics? The flow of air over a wing? What other invisible forces are just waiting for us to describe them with these incredible numbers?
Please give your opinion in the comments section. Do like the video and share it with your friends. Last but not least, subscribe to The Animated Scholar.